Well, good evening, everyone. Welcome to the RASC Winnipeg Center's first of 2021, our beginner session. And just for anybody who may not know how it works on a Zoom meeting, if you have questions or that for our presenter tonight, if you look down on the bottom of your screen, right now, there's a little thing that says chat. And what we ask is that if you got a question, just click on that box, type in what you want to ask, and then there's a few of us that'll be monitoring in that, and then we'll bring it to Scott's attention, who will be our first presenter. So again, welcome everybody. Glad to see everybody. We've got 32 people on tonight, and it's a really good start for the evening. So we'll get started here. I want to introduce Scott Young. He's a longtime member of the Winnipeg Center. He works at the Manitoba Museum Planetarium, and Scott has served on the Center Council in various capacities and was the RASC National President from 2006 to 2008. He enjoys deep sky sketching, planetary video imaging, and the occasional bit of scientific observer. Please help me and join me in welcoming Scott Young, our presenter tonight. Over to you, Scott.
All right. Well, hi, everyone. I hope you can hear me. We're going to be going through the beginner's session, which is a sort of a pre-meeting that starts at 7 o'clock. And the idea is this part will be very introductory for people that are just starting out in astronomy, whether they're starting out with just a desire, or they're starting out with a new telescope, or they're starting out with whatever. We're going to have people at all different levels participating here. This is a series, and what we'd like to do is find out from members, particularly if you enjoy the beginner session, let someone on council know, or just drop it in the chat and say, hey, how about a beginner session on blah, 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 eyepieces, something like that. It could be gear related, it could be content related, it could be how to find things in the sky, any of that kind of stuff that you as a relatively new person would like someone to share their knowledge on. And what we'll be doing is we'll be rotating through a number of presenters, and we'll get the appropriate people to do the presentations. There's a small group on council that's sort of going to be spearheading the beginners session, including Judy Anderson and Bryan Stach and myself. So you can talk to any one of us, either at the meeting or afterwards at Boston Pizza or things like that, and we can go from there. Okay, so what I'm going to do here is, hope this will work. There we go. Okay. So what is it about the night sky that gets people interested? I mean, for me, I'm very lucky. I can point to a very specific event, the total solar eclipse of 1979, and I can say that was the moment I became enamored with astronomy. For other people, it may be a single event like that, or it may just be a lifetime of curiosity. It may be something you've seen in the sky, or a show you saw, or something like that. And so we all come to this idea thinking, okay, I want to do astronomy, backyard astronomy, as a hobby. What does that mean? Well, often it means observing. Sometimes it means getting into gear. Sometimes it means sharing the sky with other people. Sometimes it means astrophotography. It can mean so many different things. And that's part of it's easy to get overwhelmed when the entire universe is your subject matter, right? So we're going to go through a couple of different things that are, good targets for beginners. We're going to talk a little bit about how to sort of start your backyard astronomy career. I'm going to issue the challenge. I know it's cold. When the sky is cold like this, the skies are the best. So try and bundle up and get outside and start some observing if you haven't yet, or if you're just still relatively new. The moon is a target that you can observe with any optical instrument. Just your eyes, just a pair of binoculars, a small telescope, a large telescope. It rewards pretty well every kind of view. We hear about the supermoon. The moon is always super, every single night. So don't wait for, particular times or someone to tell you when to go out. Anytime you can see the moon, that's a good time to observe it. And it's amazing. I mean, I know a lot of Deep sky observers, of course, just view the moon as a source of light pollution, but it is the only world in our solar system that we can see detail on with the unaided eye. So it's pretty special, and it never disappoints. If you get a new telescope, and if you get a new telescope, it's going to be cloudy that night because that's just the way it goes. But if it's not cloudy and the moon is not up, you might want to wait and have your first view through your new telescope of the moon, because it will knock your socks off. It's tempting to go out there and want to observe something faint or something challenging or whatever, and maybe that's okay if it's not your first telescope, but the moon really is something that is undeniably beautiful, and so definitely a good thing. The other thing the moon teaches us is that we have to plan. As observers, you can't just go outside and point your telescope around randomly at some random time of the night and hope you're going to see all of these amazing sights. Observing the sky takes planning. You have to know where the moon's going to be in the sky, what time it rises, and so on. And so that's where some of the resources that we get as RASC members come in handy. Sky News Magazine, the Observer's Handbook, things like that provide a little bit of that detail, so you can at least figure out, I guess, the observer's calendar as well, where your target is going to be. Get used to that, because that planning is really a big part of being a successful backyard observer. If the moon's not out for your first telescope, but a planet is, be cautious. Don't go and look at Mars tonight as your first view through a telescope. I mean, Mars right now is very small and very far away, and frankly quite disappointing. If you're going to get up early in the morning, though, and you're going to see the rings of Saturn or the moons of Jupiter or something like that, that's fantastic. Those two planets, almost as good as the moon in terms of a first view through a telescope. Venus, Mars, some of the other objects like that, just not really the same level, the same quality of image that will amaze you necessarily. The winter sky is full of star clusters. We have everything from the M35 in Gemini. There's the Beehive cluster is starting to rise in the east now, all throughout the Milky Way up in Auriga and into Cassiopeia. These clusters of a few hundred stars. They're all relatively newborn stars. They're only, a few 100 million years old or so, just out of the womb pretty much. And they cut through light pollution quite nicely. The stars themselves are relatively bright, and so even from a suburban backyard, you'll get a decent view. If you try and look at some of the fainter things, your first night out from your backyard and your neighbor's lights are on and things like that, it can be disappointing. So again, we're trying to give you that first view that will really be impressive. Okay, the Orion Nebula. This is probably the coolest object to observe beyond the solar system in terms of just sheer beauty. Any instrument that you have shows something pretty amazing. The view through binoculars is great. You can really see the little stars down in the center and these wisps of gas and so on. And as you increase the aperture, the view just gets better and better. This is also very easy to find, just below the belt of Orion. And so it's the kind of thing that can be really one of those touchstones as you go through your backyard astronomy career. My first view, I saw Stan is out there. Stan remembers me joining as a young kid with my 60 millimeter Tasco telescope, which I still have, which still works. And I was drawing the Orion Nebula through this tiny little telescope that was wobbling around in the wind and things like that. And I've done that with Orion every new telescope that I've got, or every time I've had an opportunity to look at it with a bigger telescope. It's one of those objects that you can keep coming back to over and over and over again. Another one, for some people, the Andromeda Galaxy is a big deal. Personally, I found it disappointing in a small telescope. It just doesn't show the same level of structure and things like that in my Tasco as the Orion Nebula did. But modern telescopes actually show it quite nicely, especially from a dark sky. For me, the challenge was actually, this was the object that I figured out how to find things with. I finally figured out that you have to line up your finder scope first, I finally figured out, oh, this little periscope thing on the eyepiece flips the image around so nothing matches your star charts. I finally figured out, oh, I'm only seeing this much of the star chart at once through my telescope, and it all came together, and I was able to locate the Andromeda Galaxy with my TASCO. I felt accomplished. I felt like I had done something, but it wasn't the view necessarily so much. It was kind of a gray oval of light. It was the combination of, hey, I tracked this thing down after a long hunt, and hey, the light that is going through this telescope and bouncing up into my eyeball has been traveling for 2.5 million years. Like, this light left the galaxy before humans were humans. So, I mean, the mental aspect of backyard observing is not to be underplayed either. And so I find that when I'm going out and I'm preparing what I'm going to do for the night, I'm going to pick the objects or whatever, I don't just look at where it is. I don't just look at, what I need gear-wise or things like that. I want to know what it is. I want to know, what's the distance? How big is it? How far away? Are there planets around those stars? Are there stars forming? All that kind of information, that sort of astrophysical information, to me, turns astronomy also into very much a mental activity as well as a physical, focusing light into your head activity. Now, everybody comes at backyard observing differently, and so you may find that you're more interested in the pure visual observation of the view, or you might be someone who's more interested in capturing images and not looking through your telescope, or you might decide, I'm happy sitting here in this armchair, reading and watching shows and learning about the grandness of the universe without having to go out and look for it. All of those are valid. And sometimes we sort of see either presentations or shows or things like that, and you get a sense that there's only sort of one right way to do this backyard observing. There are an infinite number of ways. You can chart your own path. In fact, you pretty much have to, because astronomy is not a sport, for lack of a better term, that you can just buy your way into, and it's not a sport where someone else can set it all up for you and then you just come and look. It's really something that you have to learn a little bit about the sky, learn about your equipment, learn about yourself, and then put all those pieces together to be able to see things in the sky. Now, this is sort of the intro of a series of courses that I've given in the past, where we sort of walk through everything from selecting a first telescope to how to set up your telescope, dealing with eyepieces and finder scopes and all that kind of stuff. And so I'm sure that kind of stuff will all appear in the beginner session over the course of the next year or so. But I did want to just cover a few of the sort of why we observe. And that's sort of what this section is here. This is an image taken by Hubble. It's part of the Hubble Deep Field. I think this is the first one, actually, where everything in the sky except this object here, everything in this view is a galaxy. This is the one star from our galaxy that was still sort of in the way. They pointed the Hubble to the very dark, empty area of our galaxy and kept the shutter open for like 24 hours. And they detected just this endless universe. To me, it's kind of mind-blowing that you can go out into your backyard and see so much of this universe that is so massive and so amazing. And that's kind of what backyard astronomy is really about. You're exploring and discovering the universe around you when you go out with your telescope. Whether you're the first to discover something or not, that sense of discovery is still very real. I discovered, I might not have told you this story. I discovered Jupiter's moons one day. It was kind of amazing, I had a telescope and there's these little moons, and I thought, oh, that's cool. And then I observed the next night and they had moved. And I was like, I've proved that the Earth is not the center of the universe. It's amazing. I mean, Galileo beat me by 400 years, but I didn't know that at the time, so it was totally valid. Despite my efforts, I have not gotten any kind of co-author credit on any of his books. That's aside. We'll ignore that. But that sense of discovery and exploration, I think, is really, really satisfying to people. And it's part of why a lot of people do this kind of backyard observing. Now we often think, okay, telescopes. I want to get a telescope and then I can start doing astronomy. That's a little bit backwards. You actually don't need a telescope to be an astronomer. Many of you already know this, of course. You're already out there looking at the constellations, tracking things down in the sky, getting to know the way the sky moves around, observing the planets and the moon and things like that. But often people think, okay, well, when I get a telescope, I'm going to start. But then what happens is you get the telescope and you use it a couple times and then you think, oh, I'd really like a better mounting for this telescope. So when I get that, then I'm going to start. And then you're like, well, there's this really nice eyepiece I saw somebody had at the last meeting. When I get that, I'm going to start. And then, of course, you think, oh, well, maybe my telescope isn't big enough and so on. Collecting telescopes and collecting astronomy gear can be its own hobby. It's related to, but it's not the same as backyard observing. And so I caution folks not to use the equipment side of things to prevent you from ever getting to the observing part of it, unless that's what you want to do. If you're a gear person, more power to you. But it is easy to get pulled into that because all of the magazines and websites and things like that, they're all focused on which gear is better, and by association, which gear is not as good. And so if you're the person that has the not as good gear, it can be discouraging perhaps. Like I came to the RASC with my proud little 60 millimeter Tasco telescope, which was promptly named the Trash Co. because apparently at the time it wasn't a good telescope and all that. And I mean, now that I know a lot more, of course, I probably wouldn't have started with that telescope. But the point was I already had it and I used it. And that's really an important part of backyard observing as well, is to go out and use the gear that you've got, because it's actually only part of your observing system. We've got an image here of lenses and mirrors and aperture and all that kind of stuff, but that's only part of it. The other half is the very sophisticated image processing system that you have that starts here and then goes inside your head. Your eye and your brain learn how to observe, and they only learn through practice. And the great thing is that practice doesn't have to be with the best telescope. In fact, it's even better practice for your eye if you're using a telescope where you're really kind of straining to see the details, because your eye is not designed for looking through a dark tube in the middle of the night. It's designed for walking around, and then at night the only thing it really needed to be able to do is make sure a tiger didn't come and eat your face. So it's really not designed for what we're trying to do with backyard observing. But you can train it. And the more you look through whatever gear you have, the more your eye and your brain will become more trained to see the detail that is there. And so that, again, that's something that you can't really short circuit. It's not something that you can just buy a piece of gear and improve. Sure, if you have better telescopes, you'll have a better view and it'll be easier to see things. But training your eye by just brute force observing a lot can really be like having a larger telescope. It can really add to the ability that you have there. Okay, I'm going to skip a couple of slides here because we're not going to talk in this particular talk about telescope designs. We'll save telescopes for another one. This is something that I put together a little while ago because I would often get questions from people saying, okay, I've got this telescope and I took it out and I didn't see anything. And I said, well, what did you go looking for? And they would say, oh, I don't know, like the universe. That's not the way it works. There's only 4% of the entire universe that we as humans have any idea what it is. Like there's dark energy, which is, maybe Michelle can talk about this later, but it seems like it's astrophysical shorthand for, and then there's dark matter, which is, it's a little bit firmer in terms of what kinds of things it might be, exotic particles or things like that, but it's still not stuff we see through telescopes. It's dark. That's kind of the point. So only 4% of the universe is stuff that is going to be made out of matter that you and I could see from our backyard. So this is what 4% of a screen being covered by blue squares looks like. There's a lot of empty space there. And it's like that with your telescope. If you just go out there and point at random areas, it's far more likely you're going to be pointed at the empty space than you are going to be pointed at one of the blue squares of that 4% of material that, we could observe. But it's worse than that, because of that 4%, all of the matter in the universe, some of it is not giving off light. Light is what telescopes see. So if it's not giving off light, you're not going to see that particular part of the 4%. So it's actually less than that. And of course, some of that stuff is far away. So it's not just, the universe doesn't just line up outside your telescope just waiting to get into your aperture. Some of it's really far away, so it looks smaller and fainter. And so this is really what the sky looks like. And so if your telescope only covers an area like that, you really need to know what you're going to look at. So I'm going to spend just the last few minutes here before we do some questions. Oops, that was mouse wheel, yes. So you really have to go out with a plan in mind. Having a telescope is pretty much worthless unless you have a way to find things. And that way can be your memory, or it can be a finder scope that lets you point at something and then allows you to zero in on something that you can see visually. It could be a set of star charts, whether you get it in a book like, say, Night Watch by Terence Dickinson, or whether you get a piece of software like Stellarium, which is a free download where you can print your own charts and it'll tell you where the star clusters are or whatever. All of those things are ways to find stuff. You can also, of course, if you've got enough money, you can buy a computer-controlled telescope that once you learn how to set it up and so on, it'll do some of the pointing for you. So yeah, it's interesting that there's some comments on the Facebook and Zoom. Yeah, they will be out of phase, because essentially what happens, we're streaming live on Facebook right now as well as to the Zoom that is set up for members. And it goes out to Zoom, which all of you can see, and then it compresses it, sends it off to Facebook. Facebook does whatever, and then broadcasts it back out. So it's probably behind by 15 or 20 seconds. So if there's something really cool that I say that you want to catch again, just flip over to Facebook and you'll hear it again. Anyway, so yeah, finding things in the sky really does take some level of planning, and it also takes some memory. You've got to be able to learn after each session. Now, I have discovered that my memory sucks. It's terrible. So I have picked up a logbook that I write down everything that I do. Well, not everything. I write down the nights that I go out and I say, oh, I looked for M31 and I didn't find it because my telescope mount was was blowing around in the wind and it was not very stable. And then, I can go through my notes. It's actually quite rewarding to go back through those old logbooks of when I was a kid and think about just how ridiculous it was to try and do some of the things that I was trying to do with that little telescope. But it's a great way to record things and to make sure that you can learn from your experience. Now, sometimes if you're doing, imaging or electronic assisted observing, as they call it now, maybe the computer will track all of that for you. Or if you're doing live streaming, it's already recorded and out on Facebook, and you can just go back at your leisure. Find whatever way works for you. But it's pretty important when you make some of those breakthroughs to be able to remember them and repeat them. And that's sort of a key thing. So find yourself a way to record your successes as well as your failures. That'll be a big part of how you grow as an observer. Okay, we have a few minutes before the main meeting starts at 7:30. What I thought we would do is throw things over to questions from the audience. Right now we're using the chat window, so if you want to throw some questions in there. If you also would like to throw in any suggestions you have for topics, those would be of value too. The team of us will put our heads together and figure out a slate of these programs for the coming year. And so if there are any questions, I'm happy to answer them now. Kate, doesn't look like we have any questions. So I'm just going to jump forward here. I wish I had set up a poll to ask how many folks that are watching already have telescopes versus those that don't. One of the things that I encountered a lot over the fall was we were all looking at Mars, and I was doing a bunch of imaging of Mars. This is not my Mars image. This is a Hubble Space Telescope image. But people were, they would want to look through the telescopes, and they wouldn't be able to see a whole lot of detail because Mars is small and so on. They expect an image like this, but what you really get is an image kind of like this. And to your eye, those don't look the same. But actually, if you sort of compare these two images, I mean, you've sort of got this sort of pointy area here and then another area that pops off to the side. The same area is facing here. We've got this little area here and a little thing off to the side. Obviously, it's not as high resolution, but you've got your polar cap down here. You got your polar cap over here. There's sort of a bright area right about there. Yeah, there's the bright area. That's the Hellas Basin in Mars right there. Used to be an ancient impact site that's all filled in with sand. Yeah, I can see that in my image too. People will have these expectations based on, either various shows or the amazing, I still call them photographs, the amazing images that people are taking with digital cameras. I mean, we have some world-class astrophotographers in this group that are doing some amazing stuff. And so it's easy to sort of think, oh, that's what I'll see through my telescope. Imaging and visual, different kinds of sports. Here's Jupiter. Great image. Here's a more closer to a visual view. You can't see as much detail on the planets, but oh, look, you can see some of the moons there. So when you're looking through your telescope, first of all, make sure you're seeing everything that there is there to be seen. Look for quite a while. My buddy Stan taught me again, don't look for a whole minute. Don't look in the eyepiece for 10 seconds and walk away. Look for a whole minute. Your eye will sort of settle down. You'll start to see more detail in the fleeting moments of the good seeing. Make sure you see everything there is there, and then keep observing over time. And, a year later, when you look at that same target with that same telescope, you're going to see more because you've been training your eye, training your brain. Oh, we got a couple of great questions coming in. Oh, everybody got their keyboard all at once, which is fantastic. No, Jim asks, how's it going at the planetarium? It's going. The museum is now allowed to open up March the 4th, but the planetarium qualifies as a movie theater, and so we can't reopen the planetarium yet. We've moved online. For those of you that haven't joined us, Thursday nights at 7 o'clock, we're doing an astronomy show that's kind of like a online planetarium show. That'll be running. But thanks for asking, Jim. Let's see. We've also got, James has said, when viewing, is it possible to see color in addition to detail? On the planets, absolutely. They're bright enough that you get great color. On fainter things, it depends. The most predominant color is sort of an eerie greenish gray. If you look at the Orion Nebula, for example, this greenish gray color can't be really recreated on photographs, but it's really cool. But to see the reds, our eyes are just not that red sensitive unless there's a lot of light. So if you are looking at something really bright, or you're looking at something with a big enough telescope that it's jamming a lot of light into your eyes, you'll start to see color. I've seen color in the Orion Nebula with the Glenn Lee's old C14. I haven't done it with the current telescope, the LX200, the 12-inch. I think it's likely possible. I just haven't been able to get out there to try it. So color is definitely something that you need a big scope to be able to see on the faint stuff. And Ken says, yeah, averted vision will definitely help. Some people have better red sensitivity as well, so you might find that you get a good thing. Here's a suggestion. Beginners can learn how to use digital image processing. Yes, in an instructor-led hands-on tutorial. Yeah, we've talked about, back during Mars, we talked about doing some courses on video observing of the planets and processing and stuff like that. There's a bunch of expertise scattered around the center. And the same thing with, you get a small CMOS camera or something like that for a couple $100 and put it in where your eyepiece is, and you can take short exposures and stack them up and get some pretty cool images. And it's almost in real time. It's what they're calling electronically assisted observing. So it's kind of real time, but you're still looking at a screen. That's a great idea, and we'll definitely look at that. Oh yeah, and so Gord's asked there as well about deep sky as well as planetary. Tara has pointed out some stars are very colorful. That's a great point. I've never really been a fan of looking at double stars. I'm not sure why. I almost never think to look at them, but you're right, especially when you've got a double star with two stars right next to each other. You can see the color contrast really well. There's some really beautiful stuff. Okay, we're at the end of our point here, and I think I've covered all the questions. So again, if you have thoughts on what you'd like to see in beginner sessions, send them along. And we're also going to be doing, we're going to be trying some things over the next number of meetings where afterwards we do breakout rooms where we could have a little section where people can just chat about a specific topic. So we'll watch for some of those as well. So at this point, I'm going to try and unpin myself from the screen. And there we go. I think I have unpinned myself. So I think I'm back to you guys now. And I'll hand things back to Dennis.
Thank you very much, Scott. Just gonna do my, maybe. All right. Am I able to share screen, Scott?
Should I switch you to host, Dennis?
Oh, okay.
You should be able to share now.
I should be able to share now?
I think so.
A little pop-up that comes up asking me who can share, only host or all panelists.
Just say all panelists, and that way everybody will be able to swap around.
Okay. So when I try to share my screen, it just comes up. All right, well, at any rate, what we'll do is we'll just carry on. For some reason, I can't share my screen, but that's okay. I'm just going to call up what I'm going to, there we go. So anyway, for tonight, welcome everyone. So again, thank you very much, Scott, for that first beginner session. And tonight we're going to, I'm just going through the meeting welcome right now. Welcome everybody. I'm going to go through some announcements, and later on we have What's Up with Bryan Stach. And then Michelle Boyce will tell us all about what's new. And our main presentation tonight is Jennifer West, who will talk about the Australian Square Kilometer Array Pathfinder Telescope. Dum, 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 dum. There we go. So things, announcements, things to know about. The council, the new council has met twice now, and we've set some pretty strategic goals for ourselves to work on. And I just want to tell you a little bit about it. So first thing we're going to do is we're going to become an incorporated center. And one of our main reasons for doing that is so that we can tap into some grants and funding. We want to look at one of the things we'll be doing is reaching out to the membership to see what they want to do with Glen Lee, and if there's improvements, changes, and exactly what we want to do. If we're incorporated and we want to do some things and we need some extra money, well, then we can apply for grants and move forward on it. So bylaws. The bylaws need some significant updating. So now 3 people on the council are taking that, reviewing it. And then when it's prepared and ready, we'll either have presented at the annual general meeting for the membership to approve, or we'll have a special meeting at some time. Going along with this is an operations manual. The operations manual is based on one that Nationals drafted for us to help guide centers and how they do their day-to-day business. Then to tie all this together, we're going to go through a strategic planning process to just give us an idea of what we want to do over the next 3 to 5 years as a center. And through various membership surveys, we're going to talk to you to see what you all as members think we should be doing. I'm very pleased to say that we're going to have a light pollution abatement portion of this. And what that's for is dark skies, working. Tara's going to take this on. She's wants to work with the city of Winnipeg, make them aware of it, to see what kind of things we can do to make the city more dark sky friendly. We also, Andrew has decided he's volunteered to move youth outreach. He's very passionate about it, and he's got lots of great ideas. And for all of these different things we're talking about, we're going to need volunteers to come in and give us a hand with this as well. But Andrew's got some great ideas, lots of different ways. So we look forward to people volunteering. Public outreach. There's a focus for us to do public outreach. We're already doing quite a bit of it in Zoom with with the Boy Scouts of Canada. We're looking at maybe perhaps moving in and doing some work with Girl Guides, and then there's several other organizations that are starting to contact us. The thing is, we're going to, even when we're doing Zoom and that, we just need multiple people to be able to do presentations. There's a lot of people in this organization that have the skills to do this, and even our new members are good at stuff, and they'd be able to do some presentations. And we're prepared to assist you with a package that's already made up, and just give you the guidance so that you're able to present it to the youth and others that are looking for that. Glenlee programs. We want to start doing more at Glenlee, not just the members' night, but organize events, not necessarily for social get-togethers like our barbecue and that, but organized events so that people come out, can socialize a little bit, do a little stargazing, and just have a really, really nice evening out. Just a pitch here for the Spruce Woods Star Party. We believe as a council that it will happen. It's scheduled for the September long weekend. And if you've got questions, go to the forum or the website, and there's some information there. And Sylvia Graca and her team are promising us a super awesome weekend with clear skies, warm weather, and absolutely no rain at all. So you heard it here first, folks. That's their guarantee. Nobody's allowed to bring a new scope. Beginner sessions, Scott kind of alluded to it, not just the beginner sessions, but we're looking at breakout rooms. And we might even do them during Zoom meetings when we would have had our break, half-hour break to go and eat all our goodies and stuff. So it's something we're exploring. It's a thing in Zoom that we're not familiar with yet, but we're working on that, and we're hoping for the next meeting to be able to use breakout rooms throughout the session. We are recruiting a meeting coordinator. The job description is going to be posted on the forum and the website, or primarily the forum. Let's just stick to the forum for now. And it'll outline really what we're looking for is the person that will coordinate the speakers and just make sure they're all lined up, have access if we're still doing Zoom, access to Zoom, and things like that. With all the other things that the council's trying to do, it's a bit challenging for us to stay on top of finding people for the meetings and that. For this year, we've probably got certainly our primary speakers figured out now till the end of March. So that's going along really well. The next thing we're going to talk about just really briefly is COVID, the rules, the health, getting all tongue tied here. The health and safety rules are still in place, limit to 5. So we're not having any Winnipeg centered approved sessions, I guess, because it's too hard to control it to keep it to 5 people. So we're hoping that in the next couple of weeks it'll loosen up, and then we can start looking at some of these things that we talked about out at Glenlee that we'd like to do. It's not that we won't do stuff in other areas. Just we have Glenlee. Glenlee's easy, and we found out that in order to go to the parks, we should actually have an insurance permit, which we can get. We've just got to work with the parks to confirm that the insurance that the RASC is carrying is suitable for our needs. And we believe it is. We've just got to confirm all that. So I'm just going to look back over here. There we go. Does anybody have any questions about any of the things I just chatted about? Don't see any. So then what I'm going to do is introduce our next speaker. And our next speaker is Bryan Stach. Bryan Stach is a past president of the RASC Winnipeg, and he has a passion for astrophotography. And he's one of these people that Scott mentioned. He's another one that's quite passionate and does some very nice work. Please welcome Bryan Stach to talk about what's up.
You should be able to share your screen.
Oh, thanks, Ennis. Sorry, I had myself muted there for a second. All right, let's go share there. Okay, and here we go. Okay, can everyone see that?
Yep.
Not okay. All right. Just a minute. So I want to just double check something here. Sorry. Okay, I'm going to continue on with this. Hopefully everyone can see this. Okay, so I'm going to do the what's up for the month of February. We don't have much happening for what's going on, but let's see what we have. We do have some interesting variable star that's happening tonight, which I'm going to mention quite soon. Okay, so let's get this started. Okay, so for the planets, what do we have for the planets? The only thing that's really visible is Mars. And of course, unfortunately, Mars is shrinking in size. For the other planets, they're pretty much too close to the sun to see anything. So we'll talk more about that later.
Bryan?
One thing, sorry?
Sorry, there. We're seeing the PowerPoint, like your list of slides and things like that. We're not actually seeing the show.
Okay,
yeah, so just, do it that way.
What I'm going to do, I disconnect my dual monitor. Sorry. All right, how's that?
Much better.
Okay, thanks. I thought that was going to happen. Okay. Anyways, okay, let's going on here. Okay, let's go with the planets again. Okay, so as I mentioned earlier, Mars is the only planet that you can really see. Okay, so as for the rest of the planets, they're either behind the sun. Venus is, of course, is in front, or behind actually, and Mercury's in front. But at the end of the month, we'll begin to see Mercury again. So let's start. Okay, so this is kind of like a top view down design of what's going on, so I can explain a little bit more about what's going on in terms of the planets. So as you can see, Mercury's in front of the sun, too close to the sun to do any kind of observing, whereas Venus, Jupiter, Saturn is just behind the sun, so we won't be able to see anything there. We'll move on. Okay, we do have a conjunction in February 18th. As you can see, the moon's going to be like 4 degrees off with Mars. So that's pretty early in the evening. And of course, we still have the winter constellation Orion, which is a very nice constellation. If you are new to astronomy, you have to see M42. Of course, that's where a beginner session will come into handy. Or if we have the mentor, again, we'll have some programs outlined for you guys soon, so we can get you guys started into astronomy. All right. Now, thanks to Jay kind of posted this up in the email list last night about this website. This is a really cool website to have. He uses it. We use it all the time for the more professional astronomer that we have here. As you can see, the forecast, I don't know if you can see my mouse here. Of course, this weekend is going to be really, really cold. As you can tell, it's going to be near minus 40 degrees for the next couple of days, and it gradually will increase by next weekend, where it's going to be close to zero. Do we have any clear skies? Yes, we do. One day we know for sure it will be Monday evening, Tuesday morning, early morning. We do have some clear skies there. This weekend, we do have some clouds, some precipitation, but not much. But next weekend, where it's going to be really warm, we do have some clear skies there on Saturday. So hopefully that's going to help us out. Now, for the events that's happening in February, of course, we do have that Centauri meteor shower that's happening. It peaked on the 8th, but we might still see some burners left from up to January or February the 21st. Of course, we have the new moon this weekend, but unfortunately, it's kind of cold, probably too cold to actually head out for safety reason. Of course, February 18th, we have the conjunction of the moon. Mercury will start to come out of the sun, so we'll be able to see it. Starting February 28th, of course, we have the full moon, 27th. And of course, I do have to mention this because by the time the next meeting does happen, the Zodiacal Lights is going to be visible in the evening. I'm going to show you a picture I've taken at Arizona a while back. We'll explain more about that later. Okay, this Algol star, or some people might come to know about it as the Demon Star. I came across this. I think it's really interesting. Unfortunately, I just was outside. It is kind of cloudy. As at 6:25 p.m., the magnitude is quite bright, around 215, 2.15. But in about 5 hours, it's going to dim quite noticeably. Again, that's 5 hours later, so I'll explain a little bit more about that later. It repeats itself every 2.87 days. If you want to get exact, I'll give the exact numbers later. But it'll be bright for a very brief moment, and then it's going to dim really fast in the next couple hours. All right. Okay, where is it? Okay, it's in the constellation Perseus. I don't know if you can see it right here, but if I'm right, I should have this arrow pointing. No, I don't. All right, it didn't pop up. Okay, you're right. Here's the star in the constellation Perseus. I set this constellation at exactly 11:30 at night. That's where it's going to dim quite much, probably around 3:45, I believe. So it's going to go from basically a 2 to a 3.5. That's pretty dim. So that's going to be quite visibly noticed to us tonight. But unfortunately, it looks like it's kind of cloudy. But anyways, hopefully we'll have some clear skies, but we won't see the real difference. Oh, there's my arrow. Okay, there it is. I'll go. All right, in the constellation Perseus. Again, that's a variable star if you're not familiar with it. All right, so we'll move on. Okay, the Zodiacal Lights that I kind of mentioned earlier, it's in the first couple of weeks in March. If you're kind of new to it and you don't know anything about it, it's quite nice. I've seen it once before, a couple times in Arizona. Jay showed me. It took a while for me to actually see it because it's quite big. And if you're in a nice dark area and where there's nothing obstructing the horizon, then you should be able to see it. Again, it's a pyramid of light. So if you haven't seen it, go see it. Again, it's going to happen the first couple of weeks in March. A nice dark skies would really help. It might be, I think the comparison, of course, I have here is it's going to be about the same brightness as the Milky Way. Just kind of give you an idea about it. Basically, what is the Zodiacal Lights? It's just basically the leftover dust from the creation of the solar system. So again, here's a picture. It was taken from Arizona. You can kind of see it's kind of a pyramid here, right, with a bright center. But yeah, it's very noticeable if you're in a really dark sky. Again, that's all I have to say for what's up in February. Hopefully, I'll see you guys out there. And good night. All right, Dennis.
Looks like Dennis is back.
Okay. Do we have any questions by any chance? Or, oh, there we go. No, it doesn't look like we have any questions. Oh, yes. Okay, someone kind of mentioned about the link that I've shown to the weather website. I'll see if I can get that up a little later.
I assume I'm up next.
Yes, Brian, are you all done?
Yeah, I'm all done. I thought I mentioned that. Sorry, I thought.
No, it's okay. My computer decided to just shut down the internet completely. So
Okay. All right.
Yeah.
So someone going to mention, just before you continue on, someone mentioned about the website. It's there. It's spotwx.com if you want to see the website that I went to for the forecast. All right.
Great. Thank you very much, Brian. So our next speaker tonight is Michelle Boyce. Michelle is a physicist at the University of Manitoba working on radio image analysis through the Canadian Initiative for Radio Astronomy Data Analysis, CERDA, examining images from the Canadian Very Large Array Sky Survey, VLAS, and the Australian Evolutionary Map of the Universe, EMU survey. Please welcome Michelle Boyce.
Okay, hi. So I'm here to give some a talk on what's new. As I mentioned before, there's a lot of things of what's new. So this is almost like what Michelle likes. That's what's new, and hopefully everyone else will. This is an artist rendition here of New Horizons. About
Michelle?
40. Yes.
Sorry, we're seeing, I think, your Yahoo email screen rather than your presentation.
That's weird. I thought you couldn't see that. Okay, let me try again. Can you see it now?
Yes.
Okay, now if I can get it to work properly. Okay, good. Okay, well, there's nothing personal on the email. It's just RASC reminders. Yeah, so this is an artist's rendition of New Horizons, which is about 45 astronomical units out from the sun. An astronomical unit is the radius of Earth's orbit, so 45 Earth radii. And what you're seeing here is dust around the sun, which represents zodiacal light and some of our galaxy. So why am I showing this picture? Well, they did something interesting. They were trying to answer the question of how dark is space? And it's not as dark as you would think. In fact, there's a bunch of diffuse light throughout space. And it's interesting because Scott had mentioned, well, what can you and cannot see? Well, this actually puts limits on what we think's out there that we can't see in terms of visual spectrum. And that's because there's all this diffuse light around from which, am I still here?
Yes.
Okay, can you see me? I can't see me. Okay, so anyway, there's diffuse light that's coming from all the stuff that we can't see. So New Horizons is out far enough away from Earth's shine and zodiacal light that there's also less radiant energy coming from the sun compared to the Earth. And so it's basically 10 times darker out there than Hubble. So they use their camera called LORRI, which is on it, which is actually a Ritchie Chrétien, which I've discovered a lot of space telescopes use this particular configuration, and there's also a field flattener and some specifications below for those who like to do astrophotography. So what they did, oops, why is it? Yeah. So this is sort of showing a view where this is our galactic disk, and then these are points below and above the disk. And these are measurement sites that they pointed their camera lorry at to try to measure how dark, like to measure the diffuse light. It's not as straightforward as one thinks. They do have to subtract out starlight, zodiacal light, galaxies, and the Milky Way being the most difficult. So I had looked a bit at the research paper. It took a while to settle this into my head, but yeah, it's quite a bit of a systematics. So their estimates give you that there are about half as many galaxies as compared to what Hubble estimates were near Earth. So Hubble estimated 2 trillion, whereas New Horizons estimated about 1 trillion. I should point out that this is actually an erratum in the website where they're actually looking at diffused light measurements and not counting galaxies, but you can sort of infer this. So they call this the COB, or cosmic optical background, as opposed to the cosmic microwave background. The cosmic microwave background tells us about the early universe, and the cosmic optical background puts upper limits on just how much stuff can be out there from the diffuse light that we can observe. Okay, so let's move on to another subject involving exoplanets. Planets called super puffs, or cotton candy planets, that are Jupiter-size-like planets, but significantly a lot less in mass compared to Jupiter and Saturn. And this is somewhat puzzling. I found the first discussion of it in 2019. And at that time, they said, okay, well, for this particular Kepler-51 planets, the system is only 500 million years old. And to contrast that, our system is 4.6 billion years. So it's a relatively young system. So they surmised that the planets were formed outside the what they call the snow line, where water freezes. It's a distance out. And then they moved in to a lower orbit through some dynamics into a closer to the sun. And so I would say they're like defrosting. And so the sun warms them up and they get bigger and outgas. However, that particular theory doesn't fit all the observations they made for other places, because they're other systems, because they could be much older, for instance. So I found this article that came out January in Astrobytes, which I'm starting to like a lot. It's slightly more technical than the other websites, but still somewhat less and more concise. So what they propose is, well, maybe it's a ringed planet and it might be tilted at a certain angle to make it look bigger. So when we see it pass, occultate past the star, we notice an equivalent dip in light. And because it's a ringed planet, its core would be smaller, and the disk is going to be a lot less dense, and so it would appear as a large planet, but it's not. So what they did is something called statistical modeling using Bayesian analysis, where this is the model, and they look at all the different angles and stuff as it transits through the star, across the star, and they try to mimic the light curve as if it was passing across the star. So this is the measured light curve, and then the model predicts something like that. This is consistent with the light curve. So it does give, instead of 10 times Earth radius, now the core planet is 4 times Earth's radius, comparable to Uranus. So it gives other properties. However, one of the problems is that it's in closer to the star, this particular example that they were trying to model. And so it can't be made of ice and the model predicts a density than rock. So there's something going on there because of the temperature. So visual confirmation would be ideal. A lot of these articles I keep reading, well, as soon as the James Webb Telescope comes out, we'll be able to confirm this, we'll be able to confirm that. And so I asked the question, where are you, James Webb? Okay. So last time I went down a bit of a rabbit hole when I was looking at life on other planets. So I started looking at the chemistry. And I tend to recycle slides, so those will end up in other slides, but less detail for overview. So I took it for granted as a physicist how they determine the properties of the planets, and it's actually quite interesting. It is fairly straightforward, but unfortunately, it is there's quite a few little steps. So I'm just going to quickly go over them. You may see some technical stuff such as equations you know from high school, but you can gloss over those if you like. So let's see what we have to do to determine the mass and radius of an exoplanet. Well, first, which is interesting, we have to find the distance to the star that the planets are orbiting about. And this is called a parallax distance. So what we do is in the summer, we can measure with respect to the Earth's orbit, the angle to the star that we're interested in. Then we wait to the winter and we measure the next angle. And because we know the diameter of the Earth's orbit through a bit of trigonometry, we can tell the distance. Now, I say this is interesting because parallax is limited to a certain distance. So that tells me that exoplanet observations are not as far out as one would expect unless you see something visually with a powerful telescope. Okay, so what's next? Next, we need to measure the brightness of the star and the luminosity. Well, if you remember your old light bulb, the further you go away, the dimmer it gets. And if we know the distance, we can actually predict how bright that light bulb is. The same goes for stars. There are different types of stars, different spectral classes, but in the end, most of them have a light curve that is related to the brightness and the mass. And from that, you can actually get the mass of the star. So now we have the distance to the star and we have the mass of the star, and we need that for basic mechanics. Next, we need to figure out, according to one of Kepler's laws, the orbital period. From that, we can get the radius of the planet's orbit. So when the planet passes by the star in question, you get a dip in light. And the next time it comes down, you get another dip. And once you know that, through Kepler's laws, given here, where this is the period and the mass of the star, you can determine the radius of the orbit. So that's one key thing. And the important thing about that is, then we'll know if the planet's in the Goldilocks zone or not, and whether it's capable of having life as we know life, and et cetera. So that's an important thing. Then we use Newton's law to determine the mass of the exoplanet. Some of you may remember this from high school, but basically the force between two massive objects is proportional to the square, inversely proportional to the square of the distance between them. So we have the mass of the star. We don't have the force, but we can get that by looking at the angular velocity. When an object moves away from you and the light is shifted, just like it is shifted into the blue and when into the red, and when it's coming towards you, it's shifted into the blue. And so from this Doppler shifting, we can get an idea of the orbital speed of the system. And from that, we can deduce the force and eliminate that to determine the mass of the exoplanet. And finally, then, now that we have the mass so we now have the mass of the exoplanet, the radius of the orbit of the exoplanet, and now we can get the radius of the exoplanet by just observing the light curve as it passes, traverses across the star. And if you're asking, well, how do we know the radius of the star? Well, the star gives off radiation, which is called a black body spectrum. And long story short, from that spectrum, the power spectrum, you can determine the radius of the star. I put it at the bottom as a footnote. So that was an interesting rabbit hole to go down, and I thought I would share it because quite often when we talk about discovering planets, I take this for granted. Okay, so now exciting news out there that's going on right now, and I believe the Planetarium is also, well, they have Dome at Home, and they're discussing this also, and we'll be discussing it next week, which is quite exciting. There's an inundation of Earth probes to Mars. Okay, so we have the, this is the United Emirates probe. Is that right? Yes, and this is from NASA. And this is from China. And the interesting thing about China is they took a selfie picture. They sent out a little satellite and took a picture. So that's actually a picture of it in around Mars. So just quickly going over this, we have the Amal telescope from the United Emirates. And this is their first mission to Mars. This diagram just shows the injection from Earth orbit to Mars orbit, and then all the maneuvers they have to do to get themselves settled into orbit around Mars. It was launched July 19th, 2020, and has arrived just last week in 2021, February 9th. And they're going to study the weather cycles on Mars and try to determine why it's losing hydrogen and oxygen and contribute towards the UAE knowledge base. The Chinese mission called Quest for Heavenly Truth, literal translation, is a satellite orbiting platform and a platform for deploying a rover. Plus, as I mentioned, there was a selfie camera, and this is the selfie shot it took of itself as it was entering Mars orbit. And if they successfully land, they'll be the third country to do so, joining Russia and the US. This is a diagram of the landing sequence for the probe. It reminds me of the movie Space 1999 with the Eagle, where they come down rapidly, drop the payload, and then take off. So it's like a sky crane that lowers it. Okay. And then finally, the other is Perseverance, or nicknamed Percy. And that'll be arriving next week, I think. So almost. And it also has the similar landing technique. You can see the crane propulsion system and then the rover. And it also has a little helicopter to fly around, which is kind of cool. And it's going straight for the Jezreel Crater, meaning lake crater, because, of course, NASA's been looking for signs of life, and it's believed that this crater was perhaps once an ocean area. They can tell this mainly from the, when the ocean dries up, you see these little hexagonal clay tiles. So they see these things and they think that there was a lot of water here for a long period of time, so there could be a chance of finding life. So that's why they're heading straight to this crater. And that's an artist's rendition, of course. Okay, so that's it for what's new. If there are any questions. I am not good at, someone will have to read me the questions because I'm lost here. If there are any questions.
Nothing's come in yet, but people are probably typing.
Okay. Yeah. Yeah, I have, Scott, given, if you remember, I gave a talk on the dark universe and discussed dark matter. Dark energy is a rather tricky subject to try to put on simple terms. I'm still struggling with it. So, but it seems to have a connection with gravity in Einstein's equations. So,
well, okay. I feel better now that if you say that you're having a hard time getting your head around it, because I just sort of throw up my hands and I don't know. But, okay, we do have a question coming in. James asks, is it coincidence that all three probes are arriving at the same time, or was that coordinated?
Well, I'll try to partly answer it, but you can also probably add to it, Scott. But basically, there is a window of opportunity of when to get to Mars. If you look at these orbits, there is an ideal time where Mars is positioned and we're positioned that we can easily just transfer our orbit from there. And it is a limited window. If we just try if we try any other time, we literally have to use a lot of fuel to get to Mars. So this is the most energy efficient time. Other than that, I'm not sure. Do you have anything to add, Scott?
Yeah, no, that's basically it. It's every 26 months you have a window where you can do the quick transfer. And so if you're going to have a return flight, you have to wait 26 months on the surface to come back. Yeah.
And I've also been reading a book on New Horizons, and apparently they had a very narrow window to get that thing up and out to Pluto.
Oh, yeah.
Yeah, in their case, it was even more problematic.
There are two more questions here. Let's do the Mars one first. Has China announced their landing site?
Actually, you answered that question at Dome at Home, so I'm going to paraphrase you.
Okay.
They're going to orbit around and see where the best landing site is, and if I recall, it's sometime in May, is it not?
Yeah, they're going to, and they have a couple of ones, but they're sort of like, well, we'll tell you after it works. That's pretty much the Chinese communications plan.
Yeah, because like this diagram here, I was so confused when I was looking at this, and then I realized you had pointed out they had copied this diagram somewhere. So they're very secretive, basically, about what they're doing.
Yeah. Here's another question. Do they know the cause of the cosmic optical background? Is it from all the visible matter or another process causing it? That's from Ed.
Well, okay. So the first time someone brought that subject to me, which was 2 months ago, it was put on some website and they made it sound very mysterious. Then I saw more recent stuff, and the answer is it's nothing mysterious. It's just let's just say you're out in the middle of the country somewhere, and you're in a dark room, right? And you've managed to cancel out all the city lights and everything else, and then someone opens their beer fridge a mile down the road, and that's the light they're trying to detect, and that light is something from. So there could be galaxies or dwarf galaxies that we cannot see with our scope, but it's leaving this diffuse light. All the matter out there is leaving like a diffuse light. And we're trying to measure that diffuse light because that gives us an idea of what's out there. But they're definitely just visual objects like galaxies, rogue stars, and so forth.
Okay. And we have one more question. Ken asks, is solar wind or solar flares an issue for the Mars missions?
That's an interesting question. Okay, so solar winds and solar flares can mess up with electronics. For instance, on the International Space Station, if there is a solar event, they have to shut down their laptops because they won't work. They do have hardened electronics that do work, mission critical electronics. So probes going to Mars would have to have mission critical systems that are required for the probe to function. They will also have non-critical systems that they can shut down in case of a solar event. And the solar events are determined by space weather monitoring, which is becoming a very important factor because it affects things on Earth. All that being said, I would like to add that if you have a manned mission to Mars, that is going to be one major problem that they will have to deal with, is how to shield people from the radiation that's out there. We are protected by our atmosphere and the magnetic field around our planet. Mars has no magnetic field. Any other questions out there?
Oh, one more just came in. Judy asks, is the Sky Crane going to bring samples home and leave a rover vehicle on Mars?
I'll let you answer that because
Okay. So yeah, the Sky Crane is basically a way of landing. They keep building bigger and bigger rovers, and it's just getting more and more dangerous. They used to use airbags and bounce around, and now they're using rockets. But even with that, they can't slow down enough in the Martian atmosphere. And so they've added the Sky Crane kind of as one more shock absorber to land the thing. Now, this rover is going to collect some samples, and it's going to store those samples away. but the orbiter is not going to actually take any samples home, this particular one. So they're going to have, China doesn't like to work with other nations, and so they don't want to use American spacecraft to help transmit their data back. So they basically had to leave a communications satellite in orbit around Mars so that they could get all of their data back from their rover. They have said they're going to bring back samples, but that'll be for a future mission. Okay, and I think we're back to Dennis.
Okay, so I'll terminate the connection here. I've stopped sharing, I believe, so it's back to you.
Well, thank you very much, Michelle. That was a great presentation. So what I'm going to do here before we introduce our main speaker is I'm going to read a story. What I want to do is highlight that there's a lot of different ways to look at the sky and interpret it. I'm going to do full disclaimer here. Obviously, I am not Indigenous. However, this I find is a really interesting book. If you haven't seen it before, I'm going to try and pronounce it. Tipiskawai Kisik, Night Sky Star Stories. And I'm just going to read to you one of the stories out of this book. The author is Wilfred Buck. If you've ever heard Wilfred tell a story, he can tell this way better than I ever could. But I'll do my best. And just to give people a way to think about different ways of looking at our night sky. And this story is Adama Achasuk, the dog stars. It has been said that long ago people did not have dogs. Humans were at the mercy of their limited resources, and since they did not have animal protectors to make them aware of approaching danger, they were sometimes taken by surprise at night while they slept at their camps. Huge bears, hungry or sick animals, and even invading nations all had access to these sleeping, unguarded people. Watchmen were posted, but being only human, they were at times lazy, distracted, inattentive, and easily taken by surprise. This situation went on for years and years until one day our Natutim Uk relatives felt sorry for us and decided to help keep us safe. Our older brother, Mikum, the wolf, sent 2 puppies to live among our people, and these wolf pups quickly became our companions, protectors, and an early warning system against harm. Seeing what Mikum had done, his younger brothers, Mishakanas, the coyote, and Makasu, the fox, blessed the humans with 2 puppies of their own. They too wanted to be honored and recognized by the humans. To acknowledge the sacrifice made by our Natunuk, the Creator placed a reminder in the heavens of the dog, Little Dipper, which would forever be a guardian for humans. Polaris anchors the dog's leash, and the dogs run around the circumference of the sky camp, alert and ever on guard. Some say that the famous Dog Soldier Society of the Cheyenne people was given a dream by these protectors, and from this dream, they were shown instructions on how to protect the people when danger was imminent. The stars of this constellation, particularly those that are part of the handle of the Little Dipper, represent Mikum, which is Polaris, Mishakananis, Ildan, and Makasu, Euroldius. The 4 bull stars represent the pups that were sent to the 4 directions of humankind. Thus it was that 6 puppies from the first 3 dogs came to be with us. And from these puppies came all the dogs of the world. So, without further ado, I would like to introduce our final speaker for the night, for our main presentation, and Jennifer West, Dr. Jennifer West. So Jennifer is now a research associate at the Dunlop Institute for Astronomy and Astrophysics at the University of Toronto. She uses large radio surveys, including data from the Australian Square Kilometre Array Pathfinder, ASKAP, to study the magnetic fields in the Milky Way galaxy and across the universe. Please welcome Dr. Jennifer West.
Thank you. And it's really Nice to be back. I guess I don't know exactly who's online, but I think a lot of you probably know me. And for those of you who don't, I used to be at these meetings regularly until I moved to Toronto 4 years ago. And so I'm really happy to be here tonight, and unfortunately can't be with you all in person, but I would like to share with you some of the stuff that I've been doing over the last few years. And so yes, I'm going to talk about the ASKAP telescope, which is the Australian Square Kilometre Array Pathfinder telescope. But before I kind of get into that, I thought I would give an overview of radio astronomy in general. There we go. So everyone, I think my screen is showing up good, and
yeah, all good.
Okay, great. So yeah, I'm a radio astronomer, and I'm really fortunate to have been able to travel around the world and visit a lot of radio telescopes. Obviously not right now, but over the last few years, I've traveled a lot and visited a lot of very cool places. And so today I'll tell you a little bit about some of these places that I've been, and a little bit about radio astronomy. And then I'll finish off with talking about ASKAP and some of the really interesting, new, exciting research that's going on with that telescope. So I thought I'd start with something familiar, and this is not the greatest picture. I need to get a better photo of the Orion Nebula to use for this talk. Sorry, the constellation of Orion. But the point here is that when we look up in the sky, we're all familiar. I think everyone on this call is probably familiar with looking up and seeing stars and seeing Orion. And some of you who are into astrophotography also know that when you look at this part of the sky for a longer period of time, you put your camera on it and open up the lens and look for quite a while, you can maybe get an image that looks like this. This is a pretty amazing image of the constellation of Orion, exactly the same spot in the sky. But if we expose our camera for a lot longer, we start to see that there's an incredible amount of stuff that's happening in that part of the sky that we just can't see with our eyes. And in this case, it's because it's just too faint and too diffuse, and our eyes just can't pick it up. And so when we look with a camera for a long time, that camera can collect photons for as long as we have the shutter open, and we can see much more detail. And I think Scott at the beginning of the meeting was talking about looking at the Orion Nebula, which is right here, through a telescope. And even through a telescope, it doesn't look anywhere near the detail that we can see when we look at it with a camera. So the optical part of the spectrum is only one small part, and a lot of you have probably seen a picture of something like this. This is the electromagnetic spectrum. And the visible part of the spectrum is just this little sliver, and there's this huge range of wavelengths and photons that come from deep out in space and travel all that way and end up here at the Earth, where sometimes we can look at them with telescopes. So this diagram shows a lot of information, and there's this line up here. There's a couple different regions in this diagram which are opaque to observers on the Earth. So these sections of the spectrum are blocked by our atmosphere. So we can't see ultraviolet and X-rays and gamma rays because our atmosphere blocks those wavelengths of radiation. And we can't see a lot of the microwave and infrared, but there is this section through the optical that is transparent. And there's also this nice big section in the radio part of the spectrum that our atmosphere is completely transparent. So when we want to look at X-rays, we have to send satellites up into space, and here's a satellite. So there's some X-ray telescopes and gamma ray telescopes, and even infrared and microwave telescopes that are up in space. But radio astronomy, we can even observe during the daylight. We can observe through clouds. Our atmosphere is completely transparent to radio. We have a lot of other problems in radio, and I'm going to talk a little bit about some of those. But here's an example, another example of the Orion part of the sky. So again, here's the visible picture that we're familiar with. On the left and on the right is a microwave image of the same part of the sky. And again, you can see that there's just an amazing amount of stuff that is just invisible to us if we limit ourselves to what we can just see with our eyes. So radio astronomy opens up a whole new universe to us if we look at the sky with radio telescopes. So the problem, there's a number of problems with radio astronomy, and when I talk about ASKAP, we're starting to solve some of these problems and get to the point where we are really seeing some very spectacular things that we've never seen before. But I wanted to just step back a moment and talk about some other radio telescopes. So these are 3 of the world's largest radio telescopes, and these are steerable radio telescopes. So they're the kind that you are probably familiar with when you think of an optical telescope, that it's on a mount and you can point it around and point at anything that you want to look at in the sky. And so I just want to take an example here. This top picture is the Ethelsburg Telescope in Germany. And to give you an example of what this telescope might see, here is a galaxy. I don't remember what galaxy this is, but this is an image that that some of you here can probably take with your astrophotography equipment, or if not, this is, you know, a very nice image, but it's not out of the realm of possibility for a backyard person. If you invest some money in some equipment, you can take a picture like this. Now, the full moon for scale is about twice the size of this whole image. So this galaxy is fairly small, but it still doesn't need a really huge telescope to be able to see this kind of detail if you want to take a picture. On the other hand, a radio telescope, the biggest radio telescope in the world, which is the 100-meter, the one I showed was one in Germany, but there's another one in the US, which is called Green Bank, and it's also 100 meters. And this red circle is what we call the beam of that telescope. And when we say beam, it's the smallest amount of detail that the telescope can see. And so this galaxy would appear in the radio telescope as just one dot. We could only see one point because that's the size of the beam. And so everything within that area gets blurred together and we don't see any detail. And so for a very long time, radio astronomy, you know, this is the extent of what we saw when we looked at things in the sky, because we needed to be able to see finer amounts of detail. And so we were confined to saying how bright things were, and we could point and we could see some, you know, in some direction, we could see how bright it is. And that still gave us a lot of information, but obviously it doesn't tell us what this object looks like. And now to use this telescope, the single dish steerable telescope, because it only sees one pixel at a time, in order to take a picture, we have to move the telescope. And so this is an example. Again, some of you have probably seen pictures of this object, which is the Veil Nebula, also called the Cygnus Loop. It is an example of a supernova remnant. And this is a pretty big object in the sky. And here, this red circle shows the size of this beam of the radio telescope. And in order to take a picture, though, we have to actually scan the telescope And so there's different patterns that we can use. We can go in a spiral, or we can go back and forth and scan across that object and see how bright it is and how the brightness changes as we scan, and then we can make a picture. And so this is what this object would look like to the Green Bank telescope, the 100-meter telescope, which again, largest radio telescope in the world. And you can see this kind of a crosshatch pattern, which comes from scanning and forming the image that way. So, so for reference, if we want to see a certain amount of detail in the optical wavelengths, is something that we could do with a 10-centimeter telescope. We need, for infrared to see the same amount of detail, we would need 0.2 meter telescope. And if we go to 1 centimeter radio wavelengths, then we need a 2-kilometer telescope. And if we want to even go longer wavelengths, you know, we need a 200-kilometer telescope to be able to see the same amount of detail, or even bigger. So 2,000 kilometers, the size of the Earth, if we want to look at very long wavelengths in radio. And you can see that even 200 meters is bigger than the biggest radio telescope that we have. And all of these pose quite an engineering challenge. So some of you might have heard that this Green Bank telescope back in the 80s actually collapsed. So I've heard the stories of the people who were there and showed up in the morning and the telescope was on the ground. And so the reason for this was it basically had structural failure. The engineering, I believe it had to do with the winds, and it just couldn't stand up, and the telescope was too heavy. So this is why we're basically limited to the size of 100 meters. Now they did rebuild it, and this is what it looks like today. So this telescope does still exist. I wanted to mention that. Now we can go bigger, and some of you might be familiar with the Arecibo Telescope, which unfortunately also had a similar fate to Green Bank, and recently met its demise and actually collapsed. The instrument platform. So this big part that's hanging above the telescope itself is 300 meters across, and this instrument platform is, I forget how many tons it weighs, and it's about 50 stories. It was suspended in the air with cables. And it, unfortunately, a number of the cables broke. There was a number of earthquakes and a number of other issues, and this telescope fell to the ground. I was very fortunate to be able to visit in 2013, I think I was there. And this is me on the walkway up to the instrument platform. But the point here is that Arecibo is 300-meter telescope, and it was not built to be steerable. It was built into the ground, and the way this telescope was pointed is by actually moving the instrument platform around, but it still was restricted to only looking at a small part of the sky. It couldn't look out everywhere in the sky. Now there's a similar telescope that is built in China. It's called FAST. It's a 500-meter telescope, very similar in a lot of ways to Arecibo. But even FAST, you know, despite the fact that it looks huge compared to the 100-meter telescope, Ethelsburg or Green Bank telescopes, and it has a significant amount greater collecting area, it still doesn't approach what we need to achieve the resolution of optical telescopes. So FAST is here, 500 meters. We're still a long ways away. The kind of wavelengths that we like to look at in radio astronomy are here in the centimeter wavelengths. And so we need something much, much bigger to be able to see the amount of detail that we want to see. So some of you might also be aware that one way around this is to use a whole bunch of telescopes. And this is the Very Large Array, which is in New Mexico. And this is an alternative to one single telescope. This is called an interferometer. And so the VLA, or the Very Large Array, is 28, 25 meter dishes. There's a lot of interferometers around the world. Here's one. This is a picture that I took a couple of years ago. Maybe you can guess where this picture was taken by the little critters in the foreground. The kangaroos really like to hang out at this telescope. This is the Australia Telescope Compact Array. This is also an interferometer. It is 6 22-meter dishes. There's this Canadian telescope, which is doing a lot of great work, called Chime. Chime is also an interferometer. It's a little bit different in design, but it's 4 telescopes that are side by side, 4 half-pipe telescopes. It's also used, the telescopes are built individually, and they're used in tandem to achieve a greater resolution, a bigger size. So for an interferometer, the distance between the most widely separated telescopes is kind of like the telescope's size. And so putting 2 dishes 200 kilometers apart is pretty easy. But there's another problem with these telescopes that a lot of people don't talk about. We talk about the great resolution we can get by putting telescopes far apart. But the problem is there's all these missing bits in between. There's all these holes in the telescope. And so there's also a limit based on the shortest distance. So if that shortest distance is too big, and even this in this picture is a little bit big, these telescopes need to be touching to really fill in all the holes. There's this missing information. And that has the result that our images are never telling us the whole story. So here is an example. This is what this little gas cloud, this nebula, might look like in real life. This is the true image. If we look at it with a single dish radio telescope, we get a blurry image. So we get something maybe that looks like this. And if we look at it with an interferometer, it's not blurry. We see lots of fine detail, but unfortunately, that's all we see. And we actually don't see the extended detail that is present. So we don't get the real picture when we look with an interferometer either. And there's solutions to this. Sometimes we take 2 images from a single dish and an interferometer, and we combine them together. Or the other solution is to use a lot more telescopes and put them closer together, and we can start to fill in some of those holes. So, so I showed you a picture of this telescope already. This is the 100-meter telescope in Germany, Ethelsburg. This is a picture that I took last year when I was fortunate enough to visit. And I want to point out, though, that there's actually 2 telescopes in this picture. And the more state-of-the-art telescope is what looks like this allotment garden in the foreground, all these little sticks in the ground. This is actually a telescope. And this is a arguably better telescope than the Ethelsburg that you see here in the background. These sticks in the ground are part of a telescope called LOFAR. And LOFAR is also called the Low Frequency Array. And this is an aerial view. And what you have if you zoomed in on this, are those little sticks. And LOFAR is in Europe. It is based in the Netherlands, and it extends all across Europe. And it's basically gone back to the simplest principle of a telescope. So all these little sticks, they're the simplest radio telescope we can think of. It's just a detector. There's no dish and there's no nothing to focus. it sees the whole sky. And the way we make an image is actually in the computer. And the reason that we can go to technology like this is because computing has advanced far enough that we can create images by gathering the signals from every one of these little sticks, and we can correlate them together in our computer and create an image. And I just want to give you a quick illustration of kind of how this works. And this is the principle that all interferometer telescopes work on. So if we have this source, some galaxy that's very far away in the sky, and it's so far away that all of these telescopes are seeing this at the same position, essentially. So the light that's traveling from this object is coming in parallel waves, and they come and they hit this interferometer, and they all hit the telescope at the same time, at all the different telescopes at the same time. But if we move this object over, oops, sorry. To the other side of the sky, so say this object is rising or setting and it's not overhead, then the light that comes from this object hits the telescopes at this angle. And so there's actually a delay between when the light might reach this telescope versus the one over here. And it's that delay that allows us to construct our image. But what we have to do is we have to record the signal from every telescope very precisely with very precise timing. And then we need to take all those signals, and in a computer, we can put them together. And that's what allows us to make an image. And so here's that same object. This I showed earlier. This is the Cygnus Loop, the Veil Nebula. And this is that blurry image we got with the 100-meter Green Bank telescope. And this image on the left is what we can do with those sticks in the ground. This is from LOFAR. And it's, as you can see, there's a lot more detail visible in this image. It still has some of these little holes, and this is from the fact that this is an interferometer image. So, so together we can use these images to get a more complete picture of what's going on in these objects. But as I said, the only reason that this now works for us is because we now have computers that can take all these signals and correlate them all together. So this is a picture of one of the supercomputing centers. This is one of the supercomputers actually in Australia. This isn't one that operates LOFAR. The LOFAR has similar computing requirements. And this is actually the really the biggest barrier that we have to making really great telescope images is computing. We're making the telescope hardware is the easy part. The hard part is taking all of the signals from all the telescopes and processing all that data. And it is an enormous data problem. So now I want to talk about ASKAP. So ASKAP is the Australian Square Kilometre Array Pathfinder telescope. And ASKAP is located in a very remote part of Western Australia. I should have put a map, but if you look at Australia, there's a very large swath of Australia that is desert, and basically nobody lives there for very, for miles and miles and miles. And I think there's some of the lowest population density on Earth that live in this part of Australia. Basically, you have to fly to Perth, which is a fairly large city on the west coast of Australia. And then you have to take another flight to a much smaller town that's up the coast, and then drive 8 hours or so into the desert before you reach this telescope. This is not my picture. Unfortunately, I haven't been able to make it to actually see the ASKAP site because it's so remote. It's difficult to get to and requires some special, special requirements to even travel there, because it can actually be dangerous if you have car trouble. There's no one to come and help you, and there's no cell phone service. There's nothing out in this part of the world. And that's why they put it there, because for radio astronomy, we want to be in very remote places, not to get away from lights, but to get away from cell phones and microwave ovens and all of the radio frequency that our society generates. And unfortunately, even though we can get away from all the people, we can't get away from satellites. And satellites are becoming an increasing problem. And since this telescope was built, this telescope started construction about 10 years ago. And the construction is pretty much complete, but we're still commissioning the instrument today because, as I mentioned, the computing challenge continues to sort of plague us. But in that 10 years since it was built, the satellite environment has grown hugely and is trashing part of the bands that we observe in. And so it's actually creating a big challenge for us. Parts of the spectrum that we used to be able to look at, we can't anymore because of satellites. So that's a big problem for radio astronomy. But as I said, this data problem is a huge, huge challenge. And this telescope isn't even one of the most data intensive in the data rates that it generates, but it still generates 2.5 gigabytes of data every second. So think about how much space you have on your hard drive and how many seconds it would take to fill up your hard drive with the data from this telescope. And it's absolutely the biggest problem that we have is both collecting all of that data, and then we have to process it. And just making the images from this telescope takes as long, if not longer, than doing the observation itself. And it generates so much data that in order to catch up with the processing, sometimes we have to stop observing. And so we fill up all of the computer disks and we can't observe anymore because we have nowhere to put the data. And we're talking petabytes and petabytes of data. Now, the remoteness of this observatory is also a really big challenge. There's no power here. There's no internet. I mean, by design, we don't want there to be cell phone towers in cities. And so they had to lay everything, bring everything to the site, their own power grid, their own internet. So this is laying fiber optic cables to the town called Geraldton to transfer the data from the telescope site. But the thing that really makes ASKAP a unique telescope is this. This is the way the telescope sees the sky. This is its detector, which is basically the first radio CCD camera, if you want to think of it that way. So unlike the Green Bank telescope that has one pixel at a time, an interferometer can make a whole image at a time. And this is like an interferometer on the interferometer. So this is called a phased array feed. And it is quite a large structure. I don't know if you can see this person for scale, but this structure is more than a meter across. So here's actually a picture of it off the telescope. And this whole thing is quite large and quite bulky and quite heavy. And it's over a meter across. But it is what makes this telescope special because we can see a very large patch of the sky at once with high resolution. And so with this telescope, we're starting to get to the point where we can collect images the way we could collect them for optical astronomy. So in, I guess the 60s, we first started doing the Palomar Sky Survey, which has now been digitized, and we have images, optical images across the whole sky. We have nothing like that in radio. We don't know what most of the sky looks like in radio because we've done all sky surveys, but they've been such low resolution that we don't see individual objects. And so we're starting to reach this point now with the surveys that are happening on, both on this telescope, but also there's the VLA Sky Survey that's also happening, and that Manitoba has a big part in processing the data for these surveys. So to give you some idea of the kinds of images that we're getting, this is not from ASKAP, this is another telescope, but this is a big chunk of the sky. This is the Milky Way galaxy through the center of this image. And right here, this is a giant radio galaxy called Centaurus A. But I want you to look at this little dot right there in the middle. This is was one of the first targets we looked at with ASKAP. And in part it's because this is a familiar object to me. And we knew what it looked like with other telescopes. So it was a good target that we could use for calibration. So what we see in the middle of this image is a supernova remnant called supernova 1006. And up here on the top left of the screen is a picture I stuck in of the full moon to scale. So the full moon would fit many times across on this image. This image is about 6-degree patch of sky. So that's a pretty big chunk of the sky that we can see with one single observation. And you can't see a lot of detail in this image because it's so large and I'm showing it on the screen. But if we zoom in on little parts of this image, we can start to see that all those little dots are, for the most part, galaxies. And we are just seeing an amazing array of things that we have never seen before. And some that we have. So there have been a lot of images taken of giant radio galaxies over the years, especially with the VLA, but we've never been able to look at huge chunks of sky. We've always just targeted small little areas and looked at little individual things. But now we're starting to see the entire sky at this level of detail, which is just opening up a huge new world of cool stuff. So here's a few more examples of some galaxies that we can see around the supernova remnant, which again, this supernova remnant had been observed with the VLA, but we've never been able to see such a large area around it. So I thought I would tell you about some of the scientific discoveries that have been made so far with this telescope. And it's possible that you've read about some of these in the news or heard about them in other places because some of these have been news stories. So this is the first one. This was a brand new discovery that was made with these images, and part of it was again that we're seeing very large parts of the sky that we never knew to look at some parts of the sky with other radio telescopes. So these things were never discovered. And this is an object which were called ORCs. That stands for Odd Radio Circle. So a very imaginative name. But basically in some of these images, we started seeing these round objects and we have no idea what they are. And we still don't know what they are. So the image on the right is an optical image in the background, and the green is the ORC, the radio emission that's superimposed. And on the left, there's two more different examples of this kind of object that we've started to see in these radio images. And like I said, we still don't know what these are. They look in some cases kind of like supernova remnants. So if I go back to this image, this is what a supernova remnant looks like. And so in some cases, they sort of looked like they could be supernova remnants, but from the position that they were in, it seems unlikely, because we can look at, we expect that supernova remnants are going to be in our own galaxy. And so there's parts of the sky where it's more likely to find them than others. And this was in a place where it would not be likely to find them. And we found a whole bunch. So it seems like they're actually reasonably common. But we just never saw them before because they're too faint, and we didn't know to look in these places to try to see them. So there's been a number of suggestions, and so far, like I said, we just really don't know what these objects are. It's possible it's some kind of cloud of emission around a galaxy cluster, or maybe it's a galaxy, a radio galaxy seen end on, and just a specific orientation that makes the emission fairly faint on the sky. And so it had never been discovered before. But so far, this is still not a closed case. We don't know what these are. And we continue to discover more of this class of object. So these odd radio circles are a mystery that's still to be solved. Another mystery that maybe you've heard about is fast radio bursts, or FRBs. FRBs have been around for a while now, and Chime especially is discovering lots of FRBs. So we are very fairly convinced now. There was some period of time where it was thought, well, maybe they're just interference. There was even a paper that microwave ovens were causing these bursts, and that was true for a couple of the cases, but it's definitely not true now. We're discovering FRBs every day now. And FRBs are basically very bright, very, very short bursts of radio light that are going off at different directions in the sky. And so Chime, which is this Canadian telescope, is very good at finding them because Chime can see the whole sky and look at it once every day. But Chime doesn't actually move. It's a fixed telescope that doesn't point, and so it can only see what passes overhead. ASKAP can point, and it also can see a big chunk of the sky at once. And so that's really the ASKAP advantage for FRBs. It's not as good at discovering them as Chime is, but it's really good at localizing them. So it can actually look in the direction, and if it catches an FRB, it's able to localize it. And so that's really what ASKAP's been able to do well. And so this is just a little graphic that shows it's been able to pinpoint exactly where in these galaxies that these FRBs have been coming from. And that really is going a long way to solving the mystery of exactly what these FRBs are. We have actually now discovered FRBs coming from our own Milky Way galaxy. So it seems like there's something that happens in galaxies. There's still a lot of debate about exactly what they are. But I think, we're getting closer every day to solving that puzzle. Here's an interesting little object that showed up in some of the images so ASKAP recently, I said that ASKAP's still in commissioning. So we're still ironing out the kinks in this telescope. But we have recently undertaken a pilot survey. And so this is from this pilot survey. There's a lot of interesting little objects. And this is one that I had a look at with a student who's working with me. And this is what the radio image looks like. This really bizarre shape. We don't really, have never seen anything quite like this if you look in optical data. But if you overlay this on an image this is actually an infrared image, we find that there's 2 elliptical galaxies. So this actually might be a case of interacting elliptical galaxies. So we've seen interacting spiral galaxies in optical emission, and this might be, is likely an example of the interacting radio emission from 2 giant elliptical galaxies, which is kind of cool. Okay, so the last part of this talk, I just want to talk a little bit about the research that I'm more directly involved with. So I'm a radio astronomer, but I study magnetic fields, and this requires even more specialized images, if you will. I look at the polarization that comes from radio light. And so polarization comes from light that happens in magnetic fields. And so in order to study magnetic fields, the polarized light is a really good probe because it comes directly from spots in space where magnetic fields are strong. And so I'm part of this project called POSSUM, which is the Polarization Sky Survey of the Universe's Magnetism. And this is also part of this Serata project, which again, the University of Manitoba is a part of this, as is University of Toronto. And so POSSUM is a survey that is happening with the ASKAP telescope. We're going to look at the whole sky, or at least all the sky that that ASKAP can see, which is in the southern hemisphere. So there's a part of the north it can't see. And we want to look at the polarized light that's coming from all over the sky. So what is polarized light? What does it let us do? Well, a lot of you have probably seen this kind of demonstration before, maybe back when you were in grade school. This is a magnet with iron filings. And so if you sprinkle iron filings on top of a magnet, the iron filings line up along the magnetic field lines of that magnet. And so this shows us the shape of the magnetic field. And we can kind of do the same thing, or not the same thing, but some similar analogous thing with our radio observations. So when we have magnetic fields in space, and we have energetic particles that are spinning around in these magnetic fields, when we look at this with our radio telescope, we can kind of think of it as putting polarized glasses on our telescope. So this is a pair of glasses from a 3D movie, which works with polarization. And if you ever go to a 3D movie, when we can go to movies again, if you steal a pair of those glasses, they're kind of fun to play with. Look at your computer monitor, look at yourself in the mirror and try closing your eyes in different ways. It's really kind of you can play some neat games with these glasses. But basically, if we put these glasses on our telescope, or we use the different polarizations that our telescope can see, we can deduce the orientation of the magnetic field, because if the magnetic field is oriented in a different direction, we see something different. And so through these observations, we can make maps like this. So this is a galaxy. This is the Whirlpool Galaxy. And these yellow little hash lines are the orientation of the polarized light that we observe with our telescope. And so through this, we're basically mapping the magnetic field of this galaxy. Here's another example of an edge-on galaxy, so we can map the magnetic fields in galaxies. So we also make use of this property. This is called Faraday rotation. And so polarized light has a particular orientation. And when it passes through space, it actually gets twisted and it's rotated. And this is called Faraday rotation. And so this is actually what we're measuring with our telescope. So we're measuring the twistedness or how much the polarization is changing as it comes to us through space. So you can kind of imagine it like this. This is the Hubble Deep Field, but you can imagine that this galaxies all have some radio emission too. And if we have our telescope and we're looking at all of these galaxies, we're actually looking at them through our own Milky Way galaxy. So our Milky Way galaxy is in the way between us and all these galaxies out in the universe. And if we look at the polarized light that's coming from all of these galaxies, they're all passing through the Milky Way. And so every galaxy that we see is actually telling us something not only about that galaxy, but also about the path that it traveled. And so it's something about the gas in our own Milky Way galaxy. And so this is what POSSUM is doing. We want to look at every single one of these galaxies and measure what's happening to that light as it travels through space. So going back to this picture of the supernova remnant, the previous number of measurements that we had like this are very small and about 1 point for every square degree on the sky. And so in this image, these colored points are all the points that we had measurements for before ASKAP started observing. And we've been able, and we will be able to do this for the whole sky. We've done this for this one little patch of sky. We can increase the number of measurements by a huge factor. And so this is now what we can measure in this part of the sky. So that's quite an improvement. And the more amount of points we can measure, the more points, the more probes we have of measuring the magnetic field through the galaxy. And that's really what I'm interested in getting at, measuring what's happening to the magnetic field in our own Milky Way galaxy. These colored points are telling us something about the direction of the magnetic field. They're telling us whether it's pointing towards us or away from us. So you can see that there starts to be patterns that we can see. Part of it's pointing towards us and part of it's pointing away from us. And from that, we can get a three-dimensional picture of what's really going on. So, yeah, how am I doing for time? So I basically have come to the end of what I want to talk about. I just wanted to leave you with one last thought, and that's this, the next frontier for us is this telescope called the Square Kilometre Array. And the SKA is going to, improve all of these observations by another order of magnitude or more. I told you that ASKAP had several gigabytes of data per second. Well, the SKA is going to have 20 terabytes of data per second. And so our computational challenge is only going to grow and grow and grow. And so part of the point of ASKAP is to get some practice and get some, get our techniques down and really understand how to work with this vast amount of data and how to operate these pipelines so that we can be ready for this next generation telescope. And so, yeah, that's all I have to say, and I'm really happy to take questions.
Thanks, Jennifer. I saw a couple of questions in the chat here, so I'll bring those back up. Tara was asking, are Chime and LOFAR adjustable like Ethelsburg or fixed like Arecibo?
Okay. Where's the question? Chime and LOFAR. Yeah. Yes. So that's right. So Chime and Loaf are both fixed. In fact, it's more fixed than Arecibo because Arecibo was able to move around a little bit. Chime and Loaf are completely fixed. They do not move at all, which makes them really cheap to build because there's no moving part. But all of the pointing is done in computers, and that's what makes them so computationally intensive.
Great, and there are more questions rolling into the chat there, so if you can just take a look at them yourself.
Yeah, sure. Any recent speculation as to what FRBs are? Yeah, so there was actually a really recent result that I wanted to escape it, but I can't. There was a really recent result. Now, this isn't exactly my area of expertise, but people I work with study FRBs, and there was an FRB that was found to be within our Milky Way, and they were able to localize it to within a supernova remnant that had a known magnetar. Now, this particular FRB was actually lower, less energy than other FRBs that we have observed in other parts of the universe. So it's not to say that all FRBs absolutely come from magnetars, but it definitely sort of points in that direction. And I was going to say that was, one of the leading, I think, ideas even before this observation, that magnetars were a fairly promising candidate of what could cause an FRB. So I think that things are sort of pointing in that direction. And also the ASKAP localizations have put them inside galaxies, and that also points to something, something fairly routine, I guess. Not that magnetars are routine; they're pretty extreme objects, but they're found all over. Okay, where did my questions go? I mentioned that computation intensity is a big issue. Is there any thinking being done about the use of quantum computing in the future? That's a good question, and I honestly have no idea. I mean, I think quantum computing has its own issues in terms of, there hasn't been a really good practical application of it as far as I understand. But, if it advances the way that we do computing, then I'm sure that we will take advantage of it. But at the moment, I think it's also a little bit unclear as to exactly how it's going to work. And so we haven't really contemplated using it in a really serious way.
Jim had asked if what attracted you to radio astronomy as opposed to visual or optical astronomy?
That's a good question. I think it's one of those things that I mean, I sort of fell into. I ended up working with some people who here in Winnipeg who work in radio astronomy, and honestly, the radio polarization as well. Early on, I sort of got involved with projects that were looking at polarization, and the polarization images are just so bizarre looking. Actually, I have one. You can still see my slides, right? Just in the. So here's the same field, but this is what the polarized light looks like in this area of the supernova remnant, and it's really patchy. Some of this patchiness is due to the telescope, but a lot of the patchiness is due just to the nature of this emission, and it's just so strange and so different that I wanted to find out what it is, and so I think that's really what got me into radio astronomy. It's also, kind of new and exciting and developing, like these images that I showed. these little galaxies here, this is the first time anyone has seen these galaxies. And if we look at, or at least seen these galaxies in this way, a lot of these galaxies have optical counterparts that are really quite boring looking. They might be just a big elliptical galaxy, and there's all this other stuff going on. So I think that's really interesting as well. Okay. Looking at the questions now.
There's another question in the chat from Lorne that says, we see that optical telescopes are using image staking to create high resolution images with only modest equipment. Do we see the same thing in radio astronomy?
Yeah, so yes, absolutely. In fact, there was a recent discovery that I was a part of. I thought about talking about it, and I don't have images handy, but one of the things that that we see, I don't know if anyone is familiar with this term, the cosmic web, but if you see large scale pictures of the universe, you see this really sponge-like web-like structure that we think the universe looks like that on really large scales. And so when we map galaxies, we see that galaxies fall along lines and filaments and chains in the universe. And so we think that matter is collecting in some non-uniform way. And so one of the people that I worked with was looking to detect the light that comes from this cosmic web. And what she did was used stacking to get a detection of this. And so she took hundreds of thousands of galaxies and stacked them all on top of each other, and was able to detect this very, very faint emission that comes, that we think exists between galaxies. So this intergalactic emission. So yeah, absolutely. And stacking is used in other kinds of radio astronomy as well. I guess that's it for questions. What frequency does ASKAP study? So ASKAP has the ability to look at a fairly broad range from around 700 megahertz up to about 2 gigahertz. But at one time, we can only look at a smaller part of that window. And so part of this pilot study that we're doing is trying to find the best window to look at. I was mentioning satellites. The satellites have really, in the last decade, have started to explode around 1200 megahertz. And that is becoming really problematic for astronomy. So a lot of radio astronomy is done around 1400 megahertz. And that's because there's a special line, an emission line from hydrogen gas that emits at that frequency. So it's actually a protected part of the spectrum, but it's a fairly narrow protected part. And so satellites are starting to crowd in around that part of the spectrum. And so before we could observe for maybe 300 megahertz around that part, and now it's down to about 140 that we have. And so our, the amount of frequency coverage we have is kind of shrinking, which is unfortunate because a lot of the studies that we do depend on how the brightness of things changes as we change the frequency. And so if we have a smaller frequency window, it becomes harder to learn things. So radio astronomy is really fighting the same light pollution battle that optical astronomy is. It's just it's not as visible because it's all in satellites and wireless communication. There's a virtual Boston pizza.
There is a virtual Boston Pizza. Yes.
Well,
There you go. Last chance for any questions for Dr. Jennifer West. Well, Jennifer, thank you very much. It was a very entertaining, very enlightening meeting. Thank you very much. I see applause. Thank you. Great talk. Lots of great comments. Thank you again. It was a wonderful, wonderful talk tonight. Appreciate you presenting, and we invite you to join later. You have to log into the different webinar, because it's not a webinar for the Boston Pizza. So for everyone, we'd just like to welcome you all to come to that. And just before you go, Jennifer, I know one of the things that the new council is working on is really strengthening relationships with like-minded organization. Do you think there's some things that we might be able to do with the Dunlop Observatory?
so I have to clarify that I'm not part of the Dunlop Observatory.
Oh, okay.
So I think people have heard of the David Dunlop Observatory, and it's the same donor. It's the same origin, obviously, but the Dunlop Institute is a separate entity from the Dunlop Observatory. Now, that being said, the Dunlop Institute is has a very strong outreach component, and I mean, off the top of my head, I don't know exactly what projects we could conceive of, but they're very open, and we're very open to that kind of thing. In Toronto, there's the Toronto RASC comes out to some Dunlop events, and we do some planet gazing parties and things like that. Now, obviously, it's it's a different connection with the RASC Winnipeg or national, but yeah, I mean, if we can think of some ideas, I'm sure we're receptive to that. So I don't know if that helps, but yeah, like I said, off the top of my head, I'm not sure what that would look like, but I think it's definitely something that we would consider.
Oh, thank you. Well, good night, everyone. Thank you all for coming, and I hope you enjoyed this evening, and you all have a great evening. And for those that are joining Boston Pizza,